Hi, Bilal. Kelvedon Barracks. Hi. Today, I'm welcoming BPHARM weekend for revision. Just tell me BPHARM. But all my students, I say hi. Today specifically for BPHARM weekend. We cannot see you, madam. No, I want you to see the board. Kindly. You'll see me. Don't worry about the face. I'm fine. Kelvo. For now, we just we share the link so that people can come on board. Hi, all my students who can see me. As much as you can hear my voice, don't worry. Hello. Yeah, thank you so much. So let's focus on the board, the whiteboard. It shall be well. Let's as we keep on coming on board. BPHARM weekend, my students, we need to revise population genetics specifically so that we can get much on whatever we didn't get during the class time. But I say hi to all my students. This far, I thank you all. Your efforts and mine will pay off someday. So for the students who have also done and they've succeeded, I thank you. Just come on board and say, oh, madam, I passed. That's what blessings are all about. So I'll be very happy and humbled when I see such comments. But still, you can give the students wachangamke pia. Thank you. Oh, Felix. Thank you so much. Thank you so much. I'm humbled. So we can come on board. The other students as well. I just say hi. Madam says hi and Madam says thank you. Now it's 1 year old, since we started the channel, and I've seen tremendous improvement on students' performance, and that's what makes me happy. That's just enough. Yeah, I'm fine. Sayoli Jamen, welcome. Malim, hi. Augusta Sombati, hi. Please just say BPHARM, even BMLS, whoever is on board, please just say BPHARM, BMLS, MBCHB, you just say hi. But today, we are very grateful. Regards, Gift Mawira. Thank you so much. Gift Mawira, I can remember the name. I have taught many and I appreciate. Yeah, BPHARM, welcome, Margaret, Essie, welcome. So we'll take 5 minutes just to welcome people on board. The number is good. We are at 40. 5 minutes, not much. Then we'll go straight to Hardy-Weinberg equilibrium. So the students will be able to calculate from your end, and in the charts is when you'll be able to tell me the answer. So as I guide on the board, you'll be able to do the calculations from your end. Hi, Jab, Roslyn, hey, Molki. Okay, I'll pronounce it the way I see it. But then welcome all. AC, don't worry, I've seen you. Ebo Kati, welcome. Hi, everyone. Just tell them to come on board so that we can finish, and then you can have good time, because tomorrow is a week for going to work. So we do want to stay a bit longer. We have, I can't read the name, but hi. We welcome you all. I'm waiting for the class reps, the 2 class reps. So for group A and group B, when I see you, then you tell me way forward. If you need to start. Moha Jab, hello, welcome. BPHARM, today is the day for BPHARM. So even if you say hi, but I have to clarify, we have BPHARM revision. Zainab, welcome, hi. We have revision for BPHARM weekend, genetics. For my BPHARM regular, as much as I'm taking you genetics again next semester, if they are also on board, they can still say hi. My BPHARM regular whom I taught the September 2023, when you are there because you already subscribed, you can still just say hi. It's okay. Yeah, Nicholas, good. That is the first class rep group A. Oh, Nicholas, thank you. Thank you so much. Welcome. So I've seen the first class rep for group A. I'm waiting for the class rep for group B, then I'll start because we need to start. And I saw the response, so everyone got the questions. So we are just going to start. Hi, Immaculate. Your voice is very beautiful. Thank you so much, Mohajab. Yes, if you hear my voice and you hear my mom's voice, it's the same. So the genetics we are learning about now, yes. So the gene which is for the voice, I don't know which chromosome it's located on my mom's and mine. Mudoni, music, hi. Akinyi, Miriam, hi. I'm waiting for the class rep, group B, or the assistant class rep, the guy who always helped me in fixing the projector. When you always say hi, oh, very good. Now they're in. Immaculate is in. Joy, welcome. So we can proceed. We can proceed. I can't read WhatsApp. Somebody's communicating on WhatsApp. I can't read WhatsApp because I'm using my phone and then I'm reading from my laptop. So I'm sorry. If I can't read the WhatsApp, I'll be able to start. So after seeing the class reps, as the other students join, let's just start without wasting any time. We promised, and I'm happy that we are on board. My students, thank you so much for creating time for us to make it work. I know it will work. Just a few weeks, and then everything will be done. But for all the efforts which we've made, it will pay off. So we have to go straight to the population genetics. I know we did much on Friday, but now, if we do the revision, you'll be familiar with how to answer questions because my cut 2 will purely be population genetics, whatever we did for lecture 7 and 8. But for the exam, we'll have now everything. So before we could do our cut, we promised that, for the ones who are coming, welcome all. I say hi and welcome, and I don't take it for granted. I thank you all for that time. So we are starting with calculation of heterozygous. I just decided to divide them so that to subtopics. Calculation of heterozygotes, assumptions, just a bit to mention, inbreeding, chi-squared of fitness test. So there is no direct. Did I do multiple? Is there something on multiple? Multiple alleles, multiallelic, correct. So there is nothing purely for the genotypic and allele frequencies, the way we started in the lectures, but it will come in at the point we look at the inbreeding, at the point we look at the multiallelic calculations. So at that point, we'll be able to understand much that we also start by looking at the genotypic and allele frequencies. So it's just mixed up in all this, but then I purely divided them into hi, the ones who are coming, subtopics. So let's just go straight to our questions. If you look at the Hardy-Weinberg, we are going to start there. If you look at the Mendel, we already covered most of it, I think all of it. So for the MBCHB, since they were doing the cut, it seems more like the main exam. So we had to combine both so that we have one derivation. So even for that, during exams or when you're preparing for exams, you can use the whole document to have the revision. But for now, we can start on Hardy-Weinberg equilibrium. And the first question under Hardy-Weinberg, when we are calculating the heterozygous, the question says, the ability to test PTC. And what I said is, if you look at the calculation of heterozygous mostly, I mentioned in class that we are looking at the point where the couples want to go for genetic counseling. But then they have to bear in mind that some tests have to be taken or to be done. If you talk about the sickle cell, as I always like giving the example, the autosomal recessive disorders, the traces of the alleles for the sickle, remember the allele for the disease is recessive. So there are traces of it in heterozygous. So we have to test, or we have to know in this population, how many are heterozygous, because there is both the dominant allele and that recessive allele. And I said in most cases, or in all the cases, we are looking for the people who have the defect. The people who are fine, we are not interested much on them, because with them they are okay. But these few who are having a problem, the Q squared, how many are they? Or how can we get the percentage of the people who have the allele for the defect, for the disease? So that's why the question 1 says, ability to test, I think it is phenylthiocarbide, something like that, always in the lab, is due to a single dominant allele T. So the people who can test will go with T. We are not interested in those people. We are interested in the ones who cannot test. So you sampled 215 individuals. It means we talk about the total number of people in that population, N equals to 215. We start by saying N equals to 215. Is it showing? Let me see. So I need to raise it a bit higher. Yeah. It's okay. Why is it a bit dim? Tell me when you can see. Can you see? Yeah. Please tell me in the charts if you can see. Just tell me in the charts. No. Yeah, because even from my end, I don't know what's happening. Let me just adjust my camera. Yeah, still blurry. That one is okay. Now tell me what you can see, because we have to communicate. We have to be. I've adjusted it because I can see from my end. Okay, now. Yes, somebody says okay. Thank you, thank you, thank you. Mudoni? Good now. Mudoni, I need, yeah, better. Somebody says better, but I think we can see. Yeah, 215. N is, yeah, thank you. Mudoni says yes. No, not 225. Jackie, not 225, because we are going to calculate. Just check the questions. 215. Good. So we are together. We are saying the ability to test, PTC, is due to a single dominant allele T. We are in number 1. We are just started. Don't go to Mendel. Go straight to Hardy-Weinberg. We are revising population genetics. Ability to test the PTC, single dominant T. You sample 215. So we said the total number of people in the population are 215. But it says 215 individuals, and determined that 138 could do what? Could detect the beta test of PTC. We are not interested in the people who can test. We want that small percentage which cannot test. So they are saying 138 could detect the test, the beta test of PTC. So don't give me the value of P squared. You know, the wrong thing which the students do, they get 138 over 215 and again give me 77 over 215. That one you'll get mixed up. Go to the questions. It says, the statement still says, 77 could not. We are talking about Q squared. 77 could not. We are starting to do calculation, please. We need Q. Q is 77 divided by 215, but then find the square root, and you are going to calculate there. Somebody says no sound. Can you hear me? So maybe the person who says no sound, I don't know whether they can adjust. Very true. Thank you. Thank you. Can we proceed? Maybe she can try to adjust whatever is in settings from her end. Thank you so much. We are dividing and finding the square root of Q. Can we divide 77? I'm waiting for the answer there. You are going to calculate from your end is when we can involve ourselves much in understanding. So from your end, calculate 77 out of 215, then we find the square root because we need Q. The ones who cannot test, you have to go straight. When you are told to calculate the heterozygous, go straight and get the Q squared, even if you are given the value for P. We don't need P. Those people are fine. We need for the ones who have a problem. And in this case, they are saying 138 is okay. So we don't need to touch 138. Thank you. 0.358. I assume that is the answer. 358. We are waiting for somebody who is going to say no. Oh, okay. 0 point or the square root now. Thank you. Abdi just gave me the division. Okay. 0.598. Malim, is that one agreed? 0.598. 0.598. So what means the square root which we are getting is 0.358, which brings 0.598. Yes, I think everyone agrees. Correct. Now, let's look for P, because we are going to get the heterozygous 2PQ. So you can go straight and say 1 minus 0.598, then P equals to, that is 204, right? 0.402. P is 0.402. Right? Do you agree with me? P is 0.402. So the question says, is it right? I'm waiting for the chats because we are going to engage ourselves. We chat, correct. Somebody has said right. The question now says, after you've calculated the allele frequencies, thank you. So those are the allele frequencies. We said, we are talking about the allele frequencies. The Hardy-Weinberg says, P plus Q equals to 1. It should be constant in the coming generations. Thank you, everyone. That is well agreed. So we have to start by finding Q, because they are talking about 77 who cannot taste, but that is Q squared. That is homozygous recessive. Is it supposed to be a specific number of decimal points? Yes. If it in class, sometimes I'll stress on the decimal point, especially when you are looking at multiallelic. But in this case, you know, if you try to narrow it down maybe into one decimal place, there is a value you lose. But in this case, it looks rare, because if we could have done 0.6, it will still bring 0.4. But in most cases, I like when I leave it at 2 decimal points or 3, so that we don't lose any value of the digits. So at this point, it's still okay. the number, the value which you'll get will be the exact one. So many a times I'll always tell you to 2 decimal place to 3 decimal place, because mostly 1, you'll always lose a value. So like when we leave it the way it was, we'll still get to the correct answer or the exact digit. So at this point, we are saying, calculate the allele frequencies of each allele. We already have Q 0.598, P 0.402. But they are saying, and the expected genotype. Yeah, we already found Q as 0.598, P as 0.402. Expected genotypes. What do they mean by expected genotypes? So what you're going to do here is, and you are the ones who are going to calculate it. We want P squared. After getting P squared, multiply by 215. We want 2PQ. After getting 2PQ, multiply by 215. We want Q squared. After getting Q squared, multiply by 215. Those are the expected genotypes or genotypic frequencies. I'm waiting for the first one. So you just say in the chat, P squared is this. So I want us to calculate. Remember, P is this one, Q is this one. So for you to get, you have to multiply 2PQ times 215. We are calculating the expected genotypic frequencies. That is what the question is asking. Good. Which one is that? Hey mold key. Is it the first one? P squared. So just tell me there, P squared 34.7444. Just do P squared 2PQ, Q squared, I'll just write on the board. Then people can agree. If they agree together in unison that that is the correct one, then that's what we'll write. And you know, even for the expected genotypic frequencies, they should add to 215. Just as observed, add to 215. Even the expected should add to 215. So let's calculate the expected. Oh, good. P squared. 34 point. Dennis is saying 34.4. Mold is saying 34.74. Why are we multiplying by 215? That is what we did. So when you get expected, you know, immaculate. When you get expected, you have to multiply by 215. You see? Wait. 2PQ 103.2. Let me write, then I can answer. If you want expected, you have to multiply the total number of people in the population. Good. P squared 34.744. Or 34.7. Q squared 77.4. If you total, let me see. 9, 13, carry 1, 14, 15, carry 1, 10, 11, correct. So that's how we do it. That's how we do it. Immaculate when you need expected. At the time you are getting, you are calculating the inbreeding coefficient or whether the population is inbred or not, you need to calculate the expected heterozygous. When you are calculating the chi-squared fitness of test, you are going to get to calculate the expected genotypic frequencies for all the genotype. So at that point, question 2. Malim, which one is that? Could it be the one which we are already done? Or you're already in question 2? Please just wait, then I can explain to Immaculate. Thank you. So Immaculate, I'm saying OQ squared 76.8888. But then there is, okay, he meant Q squared. But it's okay because you can see the final value still brings to 215. So even the 76.88, maybe if we put the 76.88, it will still come exact. But as long as it's 215 and then the other one is 3.444, just slim. But then I'm explaining to Immaculate that we have to, when we get the expected genotypic frequencies, then we really need to multiply by the total number of people in that population. If you don't multiply by 215, at the point you are doing chi-square test or inbreeding, you are not going to get the correct answer because that is what the formula says. So when you get the expected, you have to multiply by the total number of people in the population. So we already have the answer there. The allele frequencies in question 1, we had Q 0.598, P 0.402, and then we have the expected genotypic frequencies. P squared is 34.744, 2PQ 103.2, Q squared is 77.4, or the 76.38, which Malim is saying. So you have to mention those ones. We are just trying to test if the total comes to 215. Not a must that you should write the 215, but then just answer whatever you've been told and you'll be able to mention. So at that point, until there, you'll be able to get all the marks. Question 2 says, we are still talking about calculating heterozygotes. It can be set in different ways. But what we mean here is we are looking at Q squared. Where there is a problem, that is where we look at. Where there is no problem, we don't look at that. So the question says, in 9% of African population born with a severe form of sickle cell anemia that is homozygous recessive, what percent of the population will be more resistant to malaria because they are heterozygous? For the sickle cell gene, assume Hardy-Weinberg conditions. It means all the assumptions of Hardy-Weinberg intact, no selection, nothing, no mutation, no migration, mating is random. Everything is intact. So you have to calculate the heterozygous in that population where 9% of the people are homozygous recessive for sickle cell. So at that point, the 9% which we have, you talk about 9 over 100. It means Q squared, you'll put square root 0.09. It means Q equals to what? The square root of 0.09, is it 0.3 or is it 0.03? Oh no. You are not seeing. Let me adjust it well. So, can you tell me the square root of 0. Board not visible? Is it visible now? 0.3, correct. Can you see? I think there was just a bit of disturbance. Good. Thank you. So if Q is 0.3, if you understand the equation well, you'll find that saying, oh, now what is Madame setting? We are looking for Q, the homozygous recessive, the Q squared, they are 9% of the population. So we'll find Q as 0.3, as obvious. P will be 1 minus 0.3, which is 0.7. It means 2PQ will be equal to 2 times 0.3 times 0.7. So 2PQ will be 0.42. But then you are asked the number of people. Let me see. Or what percentage, correct. So if you are asked percentage times 100 will be 42% will be heterozygous. That's how simple it is. 42% will be heterozygous. We are looking at Q squared because we are interested in that allele where there is a problem. How many people of this population will be heterozygous? Meaning, it will still be safer if the percentage is low, because we have the dominant allele and the recessive allele. But in this case, you can see the percentage is 42%. And we still have traces of the dominant. Look at that 42. Very alarming. It is very alarming at that point. Because if you try to do Q squared, and then you try to trace the allele in the heterozygous, that percentage, however high it is, and you try to relate with whatever is in Q squared, then it should be a bit alarming for that case. Now, question number 3 looks more like I repeated, did I? Oh, now I talked about 500. But then for the ones who did not understand, this one do not ask much about expected. I can still do in each one of them. So we are talking about question number 3. Allele T, for the ability to test a particular chemical, is dominant of allele small t for inability to test. 500 university students were surveyed and 58 were found to be non-testers. We are interested in non-testers. Do Q squared equals to 58 over 500. Get the square root of the digit of the number which you've divided. Whatever you'll find after dividing 58 over 500. Find the square root. That is Q. Ah, good. Felix? Yeah, we've done that one. Thank you. 0.3. It means P is 0.7, but it directly asks the heterozygous, percentage of heterozygous. 0.341. Mod key. Which one is that one? Which number? When you chat, which number are we? Did you already do 58 over 500? Okay. Arnold, just tell me. Oh, question number 3. Okay. Let me do it. Let me do so that the students can see. So we are talking about question number 3. So we say 58 over 500, then Q, square root, 58 over 500. So what was Q, Arnold? Arnold, tell us what Q was. Yeah. Good. 0.116, and then that is where you got 0.3. Let us just do it together. 3, 4. Malim said 3, 4. Arnold, that's what you said up there? 3, 4, correct. So it means P is 0.66. Meaning they want what? 2PQ. They want the number of individuals here. So you do 2PQ. What will you get? They're talking about percentage still. So 2PQ is 0.34. Just tell me if I've written something wrong so that the students can understand. So what is 2PQ? 2 times 0.34 times 0.66. Somebody can calculate, let me know. 44, thank you, Dennis, 44.88%, meaning it's 0. So 2PQ is 0.4488, which brings to 44.88%. 449448, no problem. Thank you. 44. Yeah, 44. Yes. So it is just the same. 449. Yeah. So that is how we do it. So if you are asked the number of individuals who are heterozygous, the 0.4488, you multiply by 500. If you are asked percentage, multiply by 100. If you are asked about the individuals who are heterozygous, multiply by the total number of people in that population, which is 500. So we can move to question number 4. Thank you so much. Number 4 still says, within a population of butterflies, the color brown bee is dominant over color white small b. If 81% of all butterflies are white, yeah, within a population of butterflies, the color brown capital B is dominant over white. 81% of butterflies are white. Calculate the percentage of butterflies in the population that are heterozygous and frequency of homozygous individuals. It means what? We are just working with 81%. Because they say the recessive one there is white and 81% are white. It doesn't mean that you do 19. They've said in that population, I just made my camera to fall a little bit. So they are saying in that population, capital B for brown is dominant over white. But they are saying 81% of them are white. So it means the recessive allele, that is what we are looking at. So the homozygous recessive, 81, 0.81, which brings our Q to what? 0.9. It means P is what? 0.1. Then it means 2P Q is 2 times 9 times, what am I writing? 0.9 times 0.1, meaning heterozygous will be, do the decimals have an effect there? Will it be 0.18? 0.18? Correct. So the heterozygous will be 0.18. Do they want percentage? 0.18. Do they want percentage? Let me see. Individuals, right? Calculate the percentage of butterflies. So it is 18%. And then the dominant allele there they want is 0.1. So if you know what you want, you just start by calculating and getting the correct calculations, and then you go straight and write the answers. That's how simple it is. So we can do number 5 and 6. Is it the last ones? Because the other ones could be very easy. No, the PTC is repeated. And then the thalassemia, that's a bit different. So it's 1 out of, yeah. Let's see. Question number 5 says, in humans, the rhesus factor, genetic information, is inherited from our parents, but it is inherited independently of the ABO blood type alleles. Full stop. In humans, the rhesus positive individuals, in humans, the rhesus positive individuals have the rhesus antigen on their blood cells, while the rhesus negative individuals do not. There are 2 different alleles for the rhesus factor, known as the rhesus positive and the rhesus with a small r and small h. Assume that a dominant gene RH produces the RH positive phenotype, and the recessive small r small h produce the RH negative phenotype. If a population that is in Hardy-Weinberg equilibrium, 120 out of 500 individuals are RH minus. The story is so long, but it makes you to understand which one of those is for the dominant and which one is for the recessive allele. It means for the dominant allele, we have the RH positive. And then the RH small h will be for the RH negative. So without wasting any time, the Q squared will come for the RH minus. So the Q squared directly put 120 out of 500, whatever we've been doing, and get the square root. The story can be too long, but let you not get diverted so that you don't know where we are going to and where we are coming from. But what you have to identify, which one of these is Q squared? Am I dealing with Q squared or P squared? We don't need P squared. We need Q. For us to get the heterozygous, we need the Q. So the square root for that Q squared is what we need to get. So in this case, you are going to take 120 out of the 500. Then you'll get Q. After that, minus 1, you'll get the value for P. Then you are asked, calculate the frequencies of both alleles. You are not even asked about the heterozygous. They want Q and P. Question number 6. You know, it can be in any way. Even at the time when now the question number 6 talk about how students performed in class. They're talking about 100 students. The N is 100. 96 did well. We are not interested in the ones who did well. We just say congratulations. 96 did well in the course, whereas 4 blew it totally and received a great F. We say sorry. In the highly unlikely event that these traits are genetic rather than environmental, you know, if you talk about environmental, you're talking about most factors can contribute. It's not only genetic. But they're talking in a case of being genetic, not environmental, because environmental is like all students are going to do KCSE. Even the students who go through a lot in Turkana, the one who had good life in Nairobi, all these counties where the students struggle, they study under a tree, there's some who have computers, but they are going to do one exam. That could be environmental factors, which might contribute to a student getting F. But they are assuming off. It could be genetic. So they are saying if it could be genetic, then definitely, they talk about if the highly unlikely event that these traits are genetic rather than environmental, if these traits involve dominant and recessive alleles, and if the 4% represent the frequency of homozygous recessive condition, calculate the frequency of the recessive and the dominant allele and the number of heterozygous individuals. They are saying in that exam, 4% went off, 96% passed. So of the 4%, you are saying the Q squared is our 4%. So Q is 0.04 square root, where Q will be 0. Is it 0.02 or 0.2? Not sure, but I have to ask my students. Q is 0.02, right? It means P is 0.98. So 2PQ will be 2 times 0.02 times 0.98. If you multiply with 100 students, then definitely you'll be able to get 0.2. Oh, really? Good. If 3 people have confirmed, good. So let me rectify 0.2. 0.2. So then we have 0.8, right? Then they're talking about heterozygous 2 times 0.2 times 0.8. Can you tell me? Because I don't have a calc. What will it bring to PQ? Mudan is saying yes, 0. What is 0? Or 0.32. Thank you. So we are talking about 32 individuals because there are 4 of the 100. 96 of them passed. Yes. Thank you. So that is heterozygous, meaning traces of Q are there. So you are asked the alleles. We already have 0.2, 0.8, and then the individuals, since they are 100. But then, if you look at the 100, 4%. So you are asked the heterozygous individuals. If you multiply, or they didn't ask the heterozygous individuals. I think they asked the heterozygous individuals. So if you multiply by 100, you get the 32. So there are 100 students in a class, so that's fine. Number 7, we are not going to do as much as it relates to whatever we've done for the PTC. So you'll take the ones who cannot test. Don't take the ones who can test. So get 65 over 215. I think it's the same as the first one. No, it's different. It's just the numbers which are different, but it's the same one. So look for the Q squared. I think now it has entered for the heterozygous. Yeah, characterized by reduced absence of globin chain, the thalassemia recessive disorder. When you talk about the thalassemia as a recessive disorder, 1 in 500 individuals in the Mediterranean. Understand the question, read the question, understand, digest how the formula should be. So that's how simple it is. Just by knowing the formula, I'm not off, don't worry. So we are talking about calculating the heterozygous. Get the Q squared. If it's 1 out of, divide, find the square root, get Q, get P. Hardy-Weinberg says allele frequencies should add to 1. So Q plus P equals to 1 after getting Q minus, and then you get the P. Then you go straight to the question. If it needs 2PQ, multiply. If you need the number of individuals, multiply with the total number of the people in the population. If it's need percentage, do by 100. Simple as that. Question number 9, just still the same. And this one is direct. They talk about a very large population randomly mating because all the Hardy-Weinberg assumptions, they have to be met. 40% white mice. Coloring is caused by double recessive genotype AA. Calculate the allelic and genotypic frequency of the population. So you take 40%, 40 over 100, 0.4. Find the square root, get P. We are at multiallelic. Question number 10. Kindly repeat question number 8. Yeah. Please tell me in the chat if something is not clear. Don't keep quiet. I'm here because of you people. Question number 8, I said, let me put it on the board. 1 out of 500. This is what I've said in question number 8. Q squared says, so we are going to calculate it. Q squared is 1 of the 500 are born with thalassemia. It means Q, then you can we do then 1 of the 500? Lucky, Karimi? Is it Lucy? Sorry. Can we help in understanding question number 8? Please divide and give me the square root. We can divide and get the square root. First, give me when you divide, what value do we get? We are at question number 8 for Lucy to understand. When we divide, what is in the square root? Thank you. 0.044. 0.044. Good. Thank you, Malim. Can we get the square root of 0.044? Oh, somebody says 0.45. Which one can we work with? Can we do 0.5? Can we agree, members? Okay. Do we agree with Q as 0.002? Because I'm going to write. Arnold has got 0.0. Square root is 0.447. Where does Arnold get 0.02? Oh, Arnold, where are we? Okay. Oh, you want me to do 0? Okay. Square root of 0.02. Yeah, I think that's what Arnold is telling me. Is it correct, what I rectified? Okay. 0.045. Akinyi is getting it a bit high. Akinyi, yours do not have a 0. 0.045. I want us to agree. It means P is 0.955. P is 0.955 or 956 for the ones who are saying 44. Not a big difference. I want us to agree for Lucy to understand. Good. Good. Now, the question says what? For Lucy to understand. What are the frequencies of the two alleles? They are asking for allele frequencies, and that's what on the board. You already have the Q, 0.045. We have P, 0.955. Correct. How do we know if the question is asking for Q squared or 2PQ? I think I have a problem with the basis. Lillian, we said that the genotypic frequencies, the genotypes, are P squared, homozygous dominant, Q squared, homozygous recessive, 2PQ, heterozygous. That's where we started. Thank you, Lucy. That's where we started off to make things simple. And the Hardy-Weinberg law says that the genotypic frequencies and allele frequencies should be constants in each of the generations, be it F1, be it F2, be it F7. And the genotypic frequency should be equal to 1. The alleles, you know, we talked about the dominant and the recessive allele. When we were doing the 2PQ on Friday, that was yesterday, was it that far? No, the other day, sorry, on Friday, the dominant allele, the dominant allele was represented by a P. So the P plus Q should be equal to 1. I'm trying to understand the question which you're trying to pose. Madam, at what point will I understand that I should do the Q squared? I should do the what? The finding of genotypes. Is it what the question you're asking? If you see a question which talks about the recessive allele, there is a condition they're trying to express. P is 0.955, correct. Thank you, Akinyi. So they are trying to express a condition where they are stressing much on the recessive allele. Go straight and find the square root of that. Don't go the long way. That is why we are having examples here. If you look at the pattern, and most of it, they will always touch the autosomal recessive disorders. So you will know that you need to focus on the part where there is a defect, not the part which is fine. So you will get the Q squared, and meaning that both alleles which are contributed by the father and the mother are represented there. So we need the dominant allele. Whatever is there is the genotype. You know, that's why the law of segregation was saying at the point of crossover, the gametes are forming. So we're talking about the genotypes. So the Q squared is a genotype, but they're talking about the allele frequencies. So you need to get the allele Q, the recessive allele. So when you see that, do Q squared straight. I'm trying to figure out how I can give Mwilu the answer. So as we are going to discuss, that's why I separated this one to subtopics, so that you can clearly understand based on how the structure of the question looks like. It is going to look familiar that in this subtopic or in this subsection, this is how I need to tackle these questions. I hope at the end of it, you'll be able to understand. Even before the Thursday come, we shall be able to understand something. So we are multi-allelic. We've been working with 2 alleles, but now we are going to 3 alleles. The ABO blood group system being the best example. So we are saying in question 10 that in a population of 800, thank you, Lillian, you are going to understand as we proceed. And that is why the revision is very important. For what we did not get, we'll have to get it. So don't worry. In a population of 800, N is 800. 200 are blood type A. 25 are blood type B. Calculate the alleles and the genotypic frequencies of the population. That is how simple I can ask such a question. So we need to get the P, the Q, the R. We need to get the alleles first before we can go to the genotypic frequencies. But it's multi-allelic. And I have to write the Punnett square on the board so that we can know at last what are we calculating. I said in a multi-allelic system, the male and the female, we said that the Hardy-Weinberg said the gametes have to be identical. So we agreed the male has to be here. The female come and sit here. But we are saying P, Q, and R. P, Q, and R. Meaning blood group A, blood group B, blood group O. Blood group A, blood group B, blood group O. What did I write? A, B, O. The multiallelic. Here we said it will be P squared. Here will be PQ. Here will be PR, QP, Q squared, QR, RP, RQ, R squared, such that P plus Q plus R should be equal to 1. Those are the allele frequencies. But then the genotypic frequencies we talk about P squared plus 2PQ plus Q squared plus 2QR plus R squared plus RP, 2PR equals to 1. So the question says what? The question says, will autosomal diseases and X-links be factored? Autosomal diseases and X-link be factored and calculated in the same format. I don't understand what you're saying. Malim, I don't understand what you're saying. Already, when you talk about the sickle cell, you talk about albinism, are they not autosomal diseases? Based on whatever you want, the information which you want. You know, you can use any disease, but then the best one there is always the autosomal recessive, because we want to look at the traces there, based on how the question is asked. But when you want to get that allele for that disease, you know, we are looking at the situation, not the people who are normal, but the people who are sick, the allele for the disease. And if you look at the situation of the autosomal dominant, you know, we'll be talking about P, because Q is fine. So if you talk about achondroplasia, progeria, you'll be looking at P, not Q. If you look at the thalassemias, you look at the cystic fibrosis, you look at PKU, those are autosomal recessive, the Q squared. So in this other one, you'll be able to focus on P squared. And for you to know, in that population, the heterozygous, the capital P, if you talk about the autosomal dominant disorders, and you could see the main goal when you looked at the uses of Hardy-Weinberg in calculating the autosomal dominant autosomal recessive disorders, calculation of expected genotypic frequencies, you know. So they also just get captured because we are looking at the allele for the disease. That is what we are trying to work on. That is what we want to know. And that is why they go for genetic counseling. Because if we know that in this population, majority will have the condition, then it's a bit alarming. So even for the autosomal dominant disorders, you will be able to calculate it like that, because it means the Q will be safe. You get, Malim? So the ABO blood group system, those are the allele frequencies. They have to add to 1. The genotypic frequencies need to add to 1. So while that one is there, definitely you go to the question. We talk about 800 people. We are going to do our calculations. Let's go straight and look at P squared. Here P squared is given because they said blood group A You can see P is there. So P squared is what? We have P squared, which is 200 over 800. So P is square root of what? And then they say the second one is what? Blood group B. So O is what we don't have, 25. So that is Q squared. Let me give a space. Q squared 25 over 800. We do square root. Q is, so this one is P is. So you can tell me the square root. So P is, yeah. Can we do? Evelyn, which one is that? Is it P? I think it's P. It looks like P. Just tell me that is P. So is it 0.5 after dividing or after finding the square root? Good. Is this after the square root or? Let me just write 0.5. I assume it's the square root, Eve? Okay. Thank you. Mudoni, thank you. P, good. Everyone agrees. Can we do square root for Q squared? 25 over after square root. Thank you. Thank you so much, Arnold, Eve, yeah, Lucy. So we can do square root 25 over 800. We get Q. Then we can add the 2 minus 1 to get R. Oh, good. 0.177. Q is 0.177. Now, P, let me just not do P, but I can do 1 minus 0.5 plus 0.177 plus R. No, equals to R. R equals to 1. Yeah, I should put it like that. R equals to 1 minus 0.5 plus 0.177. If we add, we'll get 1 minus 0.677. So R equals to 1 minus 0.677, meaning R equals to 0.32323. Yes, correct. Thank you. Arnold has put it there. 0.323. Correct. Now, you are the ones who are going to give me the answers for each. Thank you. Each of the genotypes, I'm going to line them there clearly so that we can see them. You are going to tell me the answer squared. So let me put them clearly. R 0.323. Oh no, did I wrap B? Did I wrap P? But then P squared is what? Oh no, no. I'm sorry. I'm really sorry. I want P squared, R squared, Q squared, 2PQ, 2QR. Remember, I should add 1, 2PR. No, I'm really sorry. I didn't know that I was rubbing P and Q, but then R is there. P is P squared 0.2, or P is 0.5. Thank you. We can do P here, 0.5, and you can give me Q. I'm sorry for that. There's somebody saying 2PQ 0.176 p squared. I skipped kindly. P squared is 0.25. Good. Let's proceed. Give me the answers so that we can add and see if it gets to 1, because it had to get to 1. Somebody with another one. 25. PR, thank you. 0.324. 0.324. Thank you. We are remaining with Q2QR. R squared and Q squared, where we started from, should give us the answer. 2QR, good. 0.114. 0.114, and then somebody will be finally adding everything so that we can see if it tallies to 1. R squared, 0.105, thank you. 0.105. Q squared was what? 2QR, 0.114, thank you. We already wrote that one. Q squared, I'm waiting, Q squared, somebody has put 0.0313. 0.0, let me go back. 0.0313. 1, because the 0.031. If we add whatever is on the board, 0.031, correct. Can we add? We see if it adds to 1. Even if it's 0.99, it's fair, but it should not be more than 1. There could be a problem with one value or at a certain point, because we decided not to interfere with the decimals. In multiallelic, I'll always direct the students, even if I don't indicate it, but then I'll always direct students to leave it at 2 decimal or 3. 1 will always, how do you generate genotypic alleles? There is no genotypic alleles, nothing like genotypic alleles. You are mixing two things in one point. There are genotypic frequencies and allele frequencies. If there is no genotypic alleles, you are mixing alleles and genotypes. Alleles are different from genotypes. So I don't know which one you're asking. Genotypic frequencies are the ones on the board. The total is exactly 1. Thank you so much. Then you did it right. So the question, I want Eve to tell me what she meant, because I think she's mixing things up. So the question is saying genotypic frequencies, correct? That is what we are doing now. You can't get the genotypic frequencies in multiallelic without calculating the allele frequencies. That's why we had to start 1 sharp. I like that one. 1 sharp. It has to be that one. If it is bad, it should be 0.9999, which comes to 1. But it should not be 1 point, then there is a problem. With the value point, which is more than 5. So if I want to explain something, sorry, not justifying. I want to explain something. In multiallelic, you start by looking at, you have to find the allele frequencies first. We said the allele frequencies are what you see there, P, Q, R. Jenny, you are there. Yes, you are welcome. The allele frequencies, Evelyn, you can see PQR are the alleles which represent the ABO blood group system. And we've seen that the P squared are 200 of the 800. You are welcome, Jenny. The B squared, which is Q, are 25 of the 800. It means those are the genotypic frequencies for those specific blood groups. But we need the allele frequencies. What is P? See, we have to get the square root. So since there are already two of them, get the square root. But then the law says any of the allele frequencies, even if they are 10, but they have to total to 1, even if they'll be having a value of 0.0000, they have to total to 1. So we already found the values of the two alleles, P and Q. What of R? Just minus from 1, you'll get P, Q, and R. Without the allele frequencies, there is no way you can get the genotypic frequencies. Because just as the math says, you are going to substitute. You already know what P is, what Q is, what R is. So we've just substituted to get the genotypic frequencies. So if what you have to know for us to get the genotypic frequencies, what you see there, we've lined the 6 of them. You saw the formula which we talked about when you want to get the gamete combinations in the dihybrid. 2 power n. Here we have how many heterozygous? There are 3. ABO blood group system, you can see the heterozygous there. 2PQ, 2QR, 2PR. So it means the combination, they have to come to 6 of them. So the genotypes, we need those ones, 6 of them. So at that point, you're talking about you have to substitute. You already know 2PQ. I hope it makes sense. Same with question 11. Do the same as we did in 10. Now, the total individuals are 1,200, 400 for BB, 100 for OO. If, in this case, you go the same direction, you have 2QR, PQR, sorry, are still there, the alleles. But now, we've been given the value of Q squared, R squared. What we are going to look for is P. So you still have to find the square root. For Q squared, I'm talking about question number 11. For Q squared, you will do 400 over 1,200 and find the square root. For R, you will do 100 over 1,200 and find the square root. After finding the square root, you'll get the individual alleles. You shall have gotten the Q, the R. Now you will get the P by subtracting by 1. Then substitute. Those are the genotypes you're seeing there. They'll still remain P squared, R squared, Q squared, 2PQ, 2QR, 2PR. Only the values will change. Same with question number 12. So if you see a multiallelic, and mostly I'll use the example of ABO blood group system because I still don't have any other example which I can use. If I can find another example, well and good. But you'll realize, no. Dennis, you only multiply by the total number of population. In the case, I can ask expected. When you see a question asking expected genotypic frequencies, even here, I can ask expected. If I ask expected, then a very good question. If I ask expected, what are the expected? Let's say here I talked about expected genotypic frequencies. Multiply this one by 800, 800, 800, 800, 800, 800. That is expected genotypic frequencies. Dennis, don't multiply, do not multiply the genotypic frequencies, the total number of population, if you're not asked expected. Or if the question do not involve the chi-squared fitness of test. If it's chi-squared, I'll need those expected. Good. Thank you. So in multiallelic, Make sure you get the allele frequencies. Then it will take you to the genotypic frequencies. If the genotypic frequencies, the question says expected genotypic frequencies, then you don't stop there. You have to multiply by the total number of population, and then you'll be able to get expected. Easy peasy, right? Hardy-Weinberg assumptions, here I will not take much time. You know, this is something which somebody can read and understand. Question number 13 talks about the effect of small population size on Hardy-Weinberg equilibrium. And I told you when we talk about small population size, genetic drift come in, because the assumption of Hardy-Weinberg says the population should be large. So at that point, you're talking about small population size. Just mention small population size, genetic drift will come in. But go straight and give me the two phenomena. The founder effect and bottleneck. Describe bottleneck. And you could see something happens. The whole population is swept away. After that, then the population will grow new again. So it means for the few people who have survived the calamity, the genotypes of the new generation will be determined by the survivors. The founder effect, I said, they move from a large population based on whichever reason which is known to them better or best. They go settle in a certain population, small population. They move from a large one, go settle somewhere. Then the founders, if one of them have a condition, when the population grows, it will be determined by the founders who had such condition. So that is what you need to discuss. The bottleneck and founder effect. When you talk about small population size, don't go about any of the stories. Then we talk about selection. We talked about selection types and selection models. So if you talk about selection types, we talk about the stabilizing, we talked about directional, we talked about disruptive. But there is a way the selection types fit in the models. So when I talk about a selection model where both homozygous dominant and recessive are selected against, it means they are selectively disadvantaged. They're removed from the system. They don't have a fitness value of 1, but have a fitness value of 0, because they will not represent their genotypes in the next generation. And the best example in this model, go straight and tell me of the sickle cell anemia. You have to mention the disease. Then come and explain the model, where we can see the homozygous dominant, the normal HB, malaria will kill them. The falciparum will go for the normal HB. The homozygous recessive will suffer from the related sickle cell disease, bacterial infection, any of those, and then they'll die. So in the population, the group which is heterozygous will survive. And even question number 15 talks about a selection model where the homozygous dominant is selectively disadvantaged. And that is the CCR5 one, which I talked about. The ones who do not have the CCR5 gene, homozygous recessive, or the ones who are not heterozygous, will die when they have multiple partners and they have sex, will die of HIV. So the homozygous dominant will be selectively disadvantaged. The heterozygous will survive because they have partial immunity. It can take them a longer time before they can die. But the homozygous recessive, they will not be infected with HIV. And I say don't try it at home. I'm describing how the model works. from the research. And even if you go deep into the CCR5, you'll see how the mutant, the 32 base pair mutant gene is related with HIV. So you'll be able to look at that. So this model fits well. You have to mention the CCR5. In the case of homozygous dominants getting disadvantaged, selective disadvantage, where you can see the homozygous recessive and the homozygous dominant selectively disadvantaged, the sickle cell will fit in. So you just have to mention the disease, describe how the model works, how the homozygous relates with the situation or the disease you're talking about, how they're going to be eliminated. Yeah, simple as that. When you talk about random mating, non-random mating, sorry, you know, Hardy-Weinberg talk about one of the assumption is the mating should be random. Don't choose whoever you want to mate with based on some phenotype. You see somebody is tall, brown, or short, black, and then you think that is what you want. No, it is going to cause interferences with the allele and the genotypic frequencies. So here you talk about the two patterns. Associative mating, where we have negative and positive associative mating. You talk about inbreeding and outbreeding and the effects of inbreeding. So you have to define what inbreeding is, genetically related. Outbreeding, genetically unrelated, the way it is defined. Associative mating based on a resemblance on a certain phenotype. So such, then you mention the effect. Remember, the effect of inbreeding and positive associative mating is the same, increase in homozygosity. The effect of outbreeding and negative associative mating is the same, increase in heterozygosity. So such things, some are easy to understand. So we can just read and understand, and we'll be able to know how to answer. Is this in relation to discordant people? Are the points in relation to what when some tests are done? Where you find that in a couple, some people test positive and the other ones test negative. Daisy, are you referring to the CCR5? Daisy? You know, if you talk about the HIV, much more of immunology come in when you look at how the virus behaves, the outer, the GP proteins. So it's much which involves. So you can't conclude much based on the part where we are talking about. So there is much more to do with also the immunology part. So in this case, we're just mentioning how the model works. But we can't justify that is what led to the discordance, yeah? So somebody was tested, but then there are couples in the house, but the other one is positive. That one, we can't go much into it. So for now, we're just talking about how the selection, you know, we talked about selection, we talk about fitness value. When we talked about the selection coming in, interfering with the genotypes and allele frequencies, we mentioned that we have to talk about the fitness. Evolution has to come in for us to understand much. We are talking about how the genotypes are represented in the next generation. Are they having a fitness value of 1 or 0? So we can just leave it at that. Inbreeding coefficient, we are almost done. This one is always very interesting. So after we've looked at the pattern of non-random mating, you know, inbreeding come handy in there. But we have please, more explanation on drift versus selection and their effects. Yes, Malim, if we talked about that one are two, those are two factors there, two assumptions of Hardy-Weinberg. So I said, if you talk about small population size, I'm answering the first part of the genetic drift. If you talk about the effects of small population size in Hardy-Weinberg, go straight and talk about bottleneck and founder effect. That is what I'm stressing. That is answering question number. Genetic drifts is answering question number 13. There talk about bottleneck and genetic drift. If you talk about selection and their effects, I'm not talking about generally selection. There has to be a model which you have to describe to the examiner. Is it the examiner? Am I the examiner or you're the examiner? I don't know. But you are describing a model. I have to be specific. I can't generally give you discuss the effect of selection. That will be too wide because we have selection types. We have the selection models, like 4 of them. So I will have to narrow it down and tell you, describe for me a selection model where such genotypes are selected against or selected for. So, you're talking about two of those assumptions. You're talking about selection, you're talking about large population size. So if you talk about large population size, where there is small population size, definitely give me the founder effect and bottleneck and a genetic drift. That is where genetic drift come in. But in selection, I'll choose. I'll have to be specific. I hope I tried to answer. We are going to calculate one of those, question number 17, to see if the population is inbred. And then for the chi-squared of fitness of test, we are going to calculate 1, which will apply to the remaining ones so that we can understand. Then I leave you people to go. So we are saying, question number 17, we are going to answer that one. Given a following population data, 135 are homozygous dominants, 40 heterozygous, 25 homozygous recessive. Remember, we haven't come across a question where we directly calculate the genotypic frequencies, where we started off when you were even in class, the easiest part of it. So we are going to do this one. They are saying that 135 is AA. And then, this one is AB. Let's put the way it is. We know it is heterozygous. Then we have 40 AB. Then 25 BB. It means they are 200, right? Can we calculate the genotypic frequencies? Just the way you see them, just divide. Genotypic frequencies, we are waiting. The first person, 135 over 200. (135 over 200). We are calculating the genotypic frequencies straight from the data which we are given. A population has 135 homozygous dominant. Thank you. 0.675 0.675. Thank you. The second one, heterozygous, kindly, is it 0. What? BB, thank you, 0.125. 0.125. And AB, somebody? I did see AB because they have to add to 1. Oh, 0.2. Thank you. 0.2. They have to add to 1, 10, 9, 10, 9, 10. Correct. Now, we are going to get allele frequencies. Allele frequencies, the genotypic frequencies. It means this one is p squared 2pq q squared. We want p. When we want p, the whole of p squared plus half, meaning p equals to 0.675 plus 0.1, meaning p is 0.775. Then q is 1 minus 0.775. Q equals to 0.225. Is it correct? Are we together until there? We said for us to get, yeah, thank you. It totals to 1. For us to get genotypic frequencies, go straight. This one is straightforward. But then when we need the allele frequencies, there are traces of P in 2PQ. There are traces of Q in 2PQ. So P will be P squared 0.675 and half of AB. And that's where I've got 0.775. Q, if you have to go the longer way, 0.125 plus 0.1. So that's fine. But now, for inbreeding, to know whether population is inbred or not, you know, you go with the hypothesis. The null hypothesis here is the population is not inbred. It is not inbred because inbreeding brings perturbations on Hardy-Weinberg. So whatever you are saying here is F, the inbreeding coefficient, is 1 minus what? Observed over expected. So the observed is this one. You see, you had 40. But where is the expected now? You already have P and Q, but then multiply by 200. So we can do the math. 2 times 0.775 times 0.225. Then you multiply by 200. We are getting the expected. Expected. We can multiply. Kindly multiply for us. Anyone? 2 times 0.775 times 0.225 times the total number of people in the population. We can multiply. Then I can see from your end. Thank you. 69.75. That is expected. This is observed heterozygotes, expected hetero zygotes. So the expected heterozygous is 65.9. Did I see it well? Let me confirm. 69.75. Sorry. 69.75. So what you do, you say F equals to 1 minus 40 over 69.75. Can we divide whatever is in bracket? That is the rule of mathematics. The bottomers will say, you'll do bracket of. Before you come to subtraction, you have to start with whatever is the bracket. So if you divide 40 over 69.75, what do we get? Somebody? 40? Divide by 69.75. Thank you. 0.573. That is not yet the answer. 0.573 minus 1. F value is, the inbreeding coefficient will come to 0.427, meaning the population is not inbred. The population is not inbred because I said when the F value is greater than 0.5, then it means the population is inbred. In that case, it means the population is heterozygous. It is less than 0.5. Simple as that. So when you see the expected, you have to multiply by the total number of people in that population after getting the allele frequencies. So it will apply for any question on inbreeding. You have to follow the same procedure until you get there. Yes? So I'm not going to cover question number 18. I'm going straight to question number 19, which will serve as example for the chi-squared of fitness test. And the question number 19 will apply for question number 20 and 21. The formula, that is. Because I know people already exhausted. I can also understand. So can we do question number 19? Or you people can choose which one can we do? 21, 20, 19. In the chi-squared, I give people opinion. They should also decide. They should also have their opinion. Let me leave that one. Chi-squared, which one do we deal with? Somebody? Can we do 19 or 20 or 21? Madam is leaving the students to choose which one do we do of the three. 21. Are we in agreement? Malim's, oh no, 19, 21. We are going to vote. Like he's saying 19. Malim said, oh, 21. Why are you making it difficult now? It's a tie, 2-2. You know, if it's a tie, I'll go for 20. 21. 19, 21. Oh, no. Class reps, what do you say? 21. I can see many people are at 21. 19. Now, since 20 is not even there, can we be on fair ground? I'll do 20 because I've seen 19 and 21. Why is 22? Did I not see 22? Ah, there is even 22. We have 21. Now I'll go with 20. Because, kindly repeat question 17. Question 17. Where should we repeat? You know, you can't just repeat because we are repeating. I want to see where you don't understand. Akin, you have to tell me where to repeat. Or I can repeat everything. But then we are trying to look at if the population is inbred. You know, inbreeding is against Hardy-Weinberg. So it means when you see the data, the HO is, or the null hypothesis is, the population is not inbred. Meaning, the population is in Hardy-Weinberg equilibrium. So when you see, you are told to calculate, if the population is inbred, what you need to do here is you have to remember the formula of inbreeding, which is up there, F equals to 1 minus bracket, oh, they're still coming, 19, 21, observed heterozygous over expected heterozygous. So it means you have to start the simple formula there. The genotypes, just calculate. Get the allele frequencies the way we've done. But now, for the expected heterozygous, oh, Tanui is requesting 19 kindly. So for expected heterozygous, you'll have to do, you just have to look at the heterozygous. It's always 2pq. So multiply the p, the allele frequencies you've calculated well. Multiply the p, the q times 2. And the total number of people in that population, multiply. Oh, so somebody is saying 19, then 21. Okay. We'll do 19, then 21. I'm explaining to Akinyi. The expected heterozygous, remember to multiply. After getting the allele frequencies, multiply by the total number of people in the population, you'll be able to get the expected heterozygous. The observed heterozygous is what you are given in the raw data, the 40 which you're seeing there. So if you do the formula 1 minus observed, which is 40, over the expected, which you've calculated, body mass, we have to start with whatever is in the bracket, divide. When we divided, we got 0.573. If you subtract by if you subtract that value from 1, you are going to get 0.427. But we said in class, and we are still saying, if a population is inbred, the F value should be greater than 0.5. This one is less than 0.427. So the population is not inbred. You have to accept the null hypothesis, simple. So many people have said, start with 19, finish with 21, no problem. Let's start with 19 so that we can accommodate all the two groups which tied. The one person said question number 22, but the person will be able to follow with the examples you are going to give. So we are at question number 19. Remember, if you see chi-squared test, you are going to calculate. You have to calculate the expected genotypic frequencies, whether you like it or not. Because the final formula will have to give us the expected. So you know the formula for chi-squared test says it equals to observed expected squared over expected. That is the formula for chi-squared test. I think my camera is shaking a little bit. So we can do the first one. Given the following population, in cats, in cats. Friendliness is determined by a dominant gene F. The recessive genotype produces an unfriendly cat, that is small f. Now, it says, the genotypes of several cats are determined to be 40 FF, 40 FF, 40 FF, then 34 heterozygous, then unfriendliness is how many? Let me check. Well, 1. So it adds to 75, right? Can we do the genotypic frequencies? We have to start there. Genotypic frequencies. Can't be able to see the formula. Dennis, can you still not see? It is observed minus expected squared over expected. So we just put the formula there. Let me see. Is it now a bit visible? Yeah. So we are starting. We can do the calculation of the homozygous dominant. So it is 75. Can we do the calculation? Just tell me the first one, 40 over 75. Remember, we are working at biallelic system, 0.533. Thank you. We are working at biallelic system, so we should have the value with a degree freedom of 1, 3.84. If the value is more than 3.84, then our population is not in Hardy-Weinberg equilibrium. Which one is this? 0.013. I assume it could be the last one. Arnold? Could it be FF, the recessive? Good. 0.0133. So it could be 0.013. We leave it at 3 decimal. Good. The middle one, the heterozygous. Somebody? Then we can get the allele frequencies. I don't see the second one. I think Arnold, no, Lucy was talking about the first one, the way Arnold already gave us. 0.453. 0.453. So it is 999. Not bad, not bad, not bad. So can we go for the allele frequencies? We want F. So this is PQ. We can do P by getting 0.533 plus, we want half of this, then 0.0, or let's get the dominant first, then we'll subtract. 0.533, half of 0.453 is what? Is it 45? Even if it is 45, but the last one is not more than, yeah. Huh? After adding? No, it can't be that. AC? Are you saying that What you are showing is heterozygous, but the value should be for the homozygous dominant. You see? Check, the small f should not be there. If it's 0.227, is it half? Arnold, is that half? 0.22? 0.227. So we can talk about P being 10, 5, 6, 0.76. Then we can give Q 0.24. Are we together? Good. So it means 5, 6. It means our P allele frequencies, P is 0.76, Q is 0. Okay. AC, that's fine. Q is 0.24. We are now calculating the expected genotypic frequencies. Expected, the same story. Can you do for me P squared? We already know what P is, 0.76, Q is 0.24. Do P squared times 75. 2PQ plus times, 75, Q squared times 75. We are going to do this one until the end. And that's why I'm saying, if we understand how this one is done, we can do 21, 22 to whatever. You just go the same procedure. You follow the same, because I'm seeing people really tired. So I can do only the 19 and then I leave. Then you can follow the same procedure. We are going to do it until the end. Question number 19. Arnold, Dennis, Essie, Eve, can we calculate whatever is there on the board? P squared. The value of P is already there. P is 0.76, remember? And Q is 0.24. Yes, correct. F is 0.76. That is P. Q is 0.24. So can we do P squared, which is 0.76 squared? Oh, which one is that, Arnold? Kindly. The P squared, I assume? 21.31. You'll tell me which one. And they have to add to 75. 21.31. Yeah? Sorry, which one? Arnold, which one? I've just written for the first one. Just tell me P squared, 2PQ, Q squared, and then we'll know. After this, I'll stop. So you are going to apply the same pattern for the other three. All. The last one, the first, Edwin says, the first is 43.32. Sorry. That's accepted, 43.32. I saw the last one. Stan saying something. 43.32, correct. The last one. Oh, 2PQ, 27. Oh, the last one, 4.32. 4.32, and then somebody has 2PQ. Kindly, 27.36. Thank you. 27.36. Does it add to 75? Because it should add to 75. Let's see. 8, 10, carry 1, 9, 10, carry 1, 14, 15. Good. People are still active. Correct. So we are going to use this formula up here. I want to see if you'll be able to see me. This was already 75. So we are going to use, for us to get the chi-squared value, we are going to do for the first one, P squared. We will do observed was 40 minus expected 43.32 squared over expected 43.32 plus 34. We are at heterozygous 34 minus 27.36 over 27.36, but then here is squared, plus the last one, 1 minus 4.32 squared over 4.32. The value which you will get there, can you see? Oh, good. Yeah, we are here. I'm trying to put it better so that the students can see. We want to see if the chi-squared value is less than 3.84 to show that it's in Hardy-Weinberg equilibrium. We accept the null hypothesis. So the people who are calculating, you do 40 observed minus, we are at homozygous dominant. The first one is homozygous dominant. The second one is heterozygous. The third one is homozygous recessive. Arnold, which one is that? The first one is? It is a 3.05. 3.05. Is it the final answer? Arnold, tell me the first one. The first one is p squared, so you tell me p squared. The second one is 4.42. You know, Arnold, I assume that's how they are going. So I'm already going to write, but you'll tell me where the problem is, if there is a problem. Plus 4.42. I'm following what Arnold is giving me. Plus, somebody, final answer is 4.42. Oh no. Arnold, why are you going to final answer and I want to write? Which ones did you get for each one of them? For the first one? Chi-squared 4.41. Good. So it means Nani has confirmed, Arnold has confirmed, Malim has confirmed, but whatever you get for each of those genotypes. So you'll be able to explain much at what point was there a difference. If you look at the genotypic frequencies of 1 to 2 to 1, which one was a bit more? Oh, the first one was 0.254. It means it was not even closer to 1. Okay, 0.0. Let me just write it so that I can see. 0.0254 plus, even if it says 0.254, not 0. 0.254. That is even not closer to 1. It's a bit far. Ah, the second one, that was fine because it remained at 2. 1.611, the last bit. I would like to see what happened there. 1.611, the last one. .611, that was the second. The last, possibly it could be 0 point, right? Oh, 2.551. 2.551. So if you can look at that, because you can see the stability of the middle. The middle is 2. So not tampered that much. The homozygous dominant is less. It means the selection might be one of the factors which lead to shifting of the genotypic frequencies. Yeah. Yes. Thank you. Okay. Yes, I rectified. Okay, let me remove the 0 so that it doesn't bring confusion. So it means you can see there the homozygous dominant is going smaller and smaller. The homozygous recessive is increasing, but you can see the stability in heterozygous. So it means the factor is, if somebody asks about what could be the reason which contributes to the shifting of the genotypic frequencies, you can talk about, okay, you can talk about, yes, thank you, Mudoni. You can talk about selection. You know, selection fits well as one of the factors which might contribute to perturbations or interferences on the genotypic frequencies. So the thing is, when you multiply, you get 4.416, and it's a biallelic system, and we have a 3.84. It is more than 3.84. So you reject the null hypothesis and you say the population is not in Hardy-Weinberg equilibrium. So it is going to apply to number 21, which the students have talked about, because I can see now people are already tired. So people need to rest. You know, this one is not different. We are just talking about dominant homozygous allele, something which you are going to get even before you can get the expected. Recessive homozygous allele. You are going to get it there before you can get the expected. But you still have to calculate the expected. So here is where you exercise the simplest formula of getting the genotypic frequencies. Somebody can even ask the genotypic frequencies, the expected genotypic frequencies, the observed genotypic frequencies. So in a hypothetical population, 500 individuals, genetic anthropologists observe the following genotype distributions. Just do as the IA did there. So the homozygous dominant 150 over 500, heterozygous 50 over, no, 300 homozygous dominant over 500, 150 over 500 heterozygous, 50 over 500 homozygous recessive. And at that point, you'll be able to follow the same procedure. When you are doing expected, it finds when you're already done the allele frequencies. Go and multiply by the total number of people in the population. In this case, it will be 500. After getting the expected, follow the same formula. Chi-squared observed minus expected over expected. Simple as that. That is how you are going to know whether population is in Hardy-Weinberg or not. So I'm sorry for not doing number 21, but we can revise with the same formula. We'll be able to get. So for now, that's enough for today. I appreciate and I thank you for turning up for the revision. I still wish you the best. Please, the two class reps, Nick and the lady in group B, kindly tell me that Thursday I can have the cuts with you people. So you need to tell me maybe by Wednesday we fix, even if it's at 5. We need to do a cut, 1 hour. We have to do it because we don't have any other time. Thank you so much. So please get back to me. You know, Nick, I will always disturb your peace if you don't get back to me by Wednesday. So you just talk about it, 2 of the groups, and then let's find a common time on a Thursday. Even if it will be late at 5, I'll be able to come so that we can have the cut. Then I can mark and have an easy time entering marks. Then I give you time to revise. All the best, my students, and may God bless. Have a good night.